So another way to tell if a series converges or diverges is what is called the integral test. Basically what we're doing is making a connection to integration and an infinite series. So first of all, a couple of conditions that have to be true. You have to have a function that's positive, so it has to be above the x-axis, it has to be a continuous function, and the function has to be decreasing. Because what we're going to be doing is finding the area underneath the curve, and we're trying to see if that approaches a particular value. If the function is not decreasing, it's actually increasing, that the integral will never approach a particular value because it's getting bigger and bigger. Okay? And what the integral test says is if the integral converges, we can say that the series converges. If the integral diverges, we can say the series diverges. So here's one example. So what we're going to do is rewrite this function, rewrite the series as a function. So we're going to call f of x be x over x squared plus 1. And we're going to go ahead and integrate this function. And my u is going to be x squared plus 1. My du is 2x dx. I'm missing a 1/2. So it's going to be 1/2 natural log of x squared plus 1. And remember, when our bounds are infinity, we have to rewrite it as a limit statement. So I'm going to do the rewrite as a limit statement all in the same step. So I rewrote this as a limit statement. I also took the antiderivative as well. So my bounds are going to be going from 1 to t. Let's plug in our bounds. So I have 1/2. I'm going to pull that out in the front. I have natural log of t squared plus 1 minus the natural log of, if I plug in 1, this becomes 2. Okay, now let's see what happens to the limit. If I plug in infinity for t, this is going to be infinity, because what happens to the natural log graph as you get infinitely bigger? Think about your log graph. It looks something like this. It does get infinitely bigger, not very quickly as you go towards infinity. So this is infinity right here. Infinity minus the number is still infinity. Infinity times a half is still going to be some infinity. So just a number with very big magnitude. So this limit ends up being infinity. So from here, we say the integral diverges. So if the integral diverges, then we can also draw the conclusion that the series also diverges. The important thing to note is that this series is not the same as the integral. They don't have the same value if they do converge, but we're going to use the integral to figure out what happens to this series. Okay? The reason is when you're looking at a series, you're only going from 1, 2, 3, 4, etc. When you look at the integral, you're adding it up infinitely from 1 to infinity, not just selected values. Okay? Let's look at one more example. So let's apply the integral test to 1 over n squared plus 1. So my function is 1 over x squared plus 1, so I'm going to do the same thing, set up my integral. I'm going to rewrite using a limit statement, and I'm going to do the antiderivative at the same time. The antiderivative of 1 over x squared plus 1 is actually your arctangent of x. And let's go ahead and plug in our bounds. So I have arctangent of t minus arctangent of 1. Here are my bounds. And now let's go ahead and evaluate. So the arctangent of t. So you're looking for the angle where the tangent graph approaches infinity. So if you think about your tangent graph, this is the piece of the graph that you need. So what happens as you approach infinity, the tangent graph is going towards pi halves. So this is pi halves, arctangent of 1 is pi fourths, so this is pi fourths. So because the integral converges, we can also make the conclusion that this series will also converge. Okay, again, be careful. This integral is equal to pi fourths. The area underneath this curve from 1 to infinity is pi fourths. It does not mean that this is pi fourths. This is incorrect. We just know that the integral converges, so we can say the series converges, but we don't know what it necessarily converges to.